Good evening. We are honored to have with us tonight Frank Donovan, W3LPL, a world-renowned contester. Frank owns a contest superstation with 4 200-foot towers and 3 150-foot rotating towers in western Howard County. He put up every tower and created every antenna himself. His antennas are fed by single-band homebrew 1,500-watt amplifiers, one for each band. Over the years, Frank's multi-operator teams have won about 1/3 of the CQ worldwide and ARRL DX contests that they've entered. Frank is also very active 6-meter DXer using mostly the FTS digital mode. Frank's ham radio story began in 1923 when his grandfather collected parts and built single tube receivers for friends and family. These parts and grandpa's expertise were 8-year-old Frank's introduction to electronics and radio during the 1950s. At age 17, he finished first place in the U.S. in the 1964 ARRL CW DX contest, low power category. Immediately after college, he joined the Air Force as a second lieutenant, but still found time to pursue his amateur radio interests, and even more so after completing his service. Frank finished first place as U.S. single operator in 4 CQ worldwide CW and 4 ARRL CW DX contests from 1973 to 1978. His first multi-operator, multi-transmitter experience was with the world high-scoring 1974 DX CW contest. Frank was inducted into the prestigious CQ Contest Hall of Fame in 1999 and is a regular presenter at Contest University and to radio clubs around the world. He retired 13 years ago as a chief engineer at General Dynamics Corporation after a 45-year career in electronics and systems engineering. In May 2021 and May 2023, Frank was awarded QST cover plaques for his articles What to Expect During the Rising Years of Solar Cycle 25 and Experience the Wonders of Solar Cycle 25's Solar Maximum. The QST Cover Plaque Award is given to the author of the most popular article in each issue. So obviously there's a lot of interest in the topic of solar cycles. And Frank, W3LPL, is obviously one of the most knowledgeable experts qualified to discuss it. Adding to his accolades, Frank was also a major contributor to the propagation chapter in the 100th anniversary edition of the ARRL Handbook. So we are thrilled to have Frank join us tonight. Thank you, Frank, for taking time to be with us. And now it is over to you.
Thank you for that introduction, Alex. See if we can do the sharing here. Okay. So, welcome everybody. This is going to go a little less than an hour, and I'll be happy to take questions either directly after the presentation, or I'm always happy to answer emails. And my email address has been the same for more than 20 years. You can either copy it down here or enter my call sign on qyz.com and you'll find my email address there. So I'll just briefly mention this image. This is an image of the sun taken during one of the previous solar maximums, and you can see a lot of solar activity, and this is typically what the sun looks like at this part of the solar cycle. So you see the sun itself. This is taken through a photographic filter, and it's showing the sun at the wavelengths of light known as extreme ultraviolet. And that's the wavelengths at which the ionization of the Earth's ionosphere occurs. So you can see the really bright areas on the surface, the visible surface of the sun, and you can see the very bright explosions taking place from the sun. So this is just every day on our own local star. Alex mentioned the articles I've written in QST. This is the most recent one. It's very readable. If you haven't read it, either take a look in your own QST or borrow one, and it's a very readable article. And very accurately portrays what we're experiencing now with solar cycle 25. For those who would like to dive deeper into the topic, there are 3 excellent publications available from the ARRL. The least expensive and most readable is the one on the right. Here to there for radio wave propagation. It's written for inexperienced or moderately experienced hams. The other 2 are excellent reference books written by people like myself who are professionals in the fields of engineering and physics, but were written for hams. So they're much more readable by non-professionals than the kind of stuff we write in the professional media. And for those who would like to dive deeper and don't want to spend the money, this is a very excellent publication that's available for free online. It is definitely written for people with a scientific background. It's readable by others, but it's a difficult read if you don't have a scientific or engineering or physics background. Okay, so this is just a list of some of the important aspects of the sun that relate to HF propagation that we enjoy as hams on the HF bands. It all originates from the sun's magnetic field, which is extremely intense, and it creates surrounding the sun its atmosphere, which is known as the corona. And the temperature of that atmosphere is millions of degrees Fahrenheit. It's incredibly hot, and it produces what is known as plasma, which is ionized gas. And because that plasma is in constant motion, it becomes magnetized. It's very conductive, so becomes magnetized plasma. Probably one of the best known features of the sun are sunspots. It's caused by the extremely intense magnetic field of the sun. And those sunspots occur in roughly 11-year cycles. We'll talk about that a little bit more. The sun's atmosphere of ionized gas, known as plasma, extends throughout the solar system, well beyond the location of the Earth, and it's known as the solar wind. It's always present. You can visibly see the solar wind if you've ever seen a comet, and the tail of a comet is caused by the solar wind, which blows the tail of the comet away from the sun. Along with the beneficial aspects that we as hams experience with the sunspot activity, there's also a variety of phenomena on the sun that cause disturbed conditions. During the course of a typical month, we might have about 20 days of relatively normal solar maximum conditions like we're observing now, and maybe 5 days out of the month that are exceptionally good. And then, unfortunately, about 5 days of the month that are very bad. And those last 3 items from the sun, coronal holes, coronal mass ejections, known as CMEs, and solar flares are some of the things that cause disturbed HF radio propagation. I'm not going to read this slide, but these are some of the concepts that every ham that's active on HF should have some familiarity with. Sunspots are probably the most important aspect of it, causing the normal or exceptionally good propagation on all but 5 days of the month. And sunspots vary in quantity and intensity on about 11-year cycle, known as the solar cycle. The beneficial radiation comes from extreme ultraviolet light. Thankfully, that radiation never makes it to the surface of the Earth. Otherwise, there'd be no life on the Earth. It gets completely absorbed by our atmosphere, and extreme ultraviolet light can be measured only in space by satellites. There's also another form of radiation, energetic X-rays, which are radiated by solar flares, which we'll talk about a little bit. They cause complete blackouts of the HF radio propagation. We'll talk about that in a little bit. On the Earth, there are disturbances known as geomagnetic disturbances. They're disturbances of the Earth's magnetic field that is caused by solar activity. We'll talk about that a little bit later. The sun rotates on a 27-day period. We'll also talk about that a little bit later and why that enhances and disturbs radio propagation on about a 27-day periodic cycle. And also there's a very significant seasonal variability. We'll talk about why that's the case. So these are all very important concepts. We'll touch on all of them in a little bit of detail. Not a great deal. It's not enough time for that, but some detail. This is what the sun looks like viewed through a filter that allows extreme ultraviolet light to pass through. So this is obviously these photographs of the future have not been taken yet. These are images that were taken during the last solar cycle, and the years that are shown on this slide represent this solar cycle, but these images are actually 11 years older than shown. But what you can see is we're in 2024 now, which we believe will be solar maximum year, and you can see that the intensity of the extreme ultraviolet light shown through these filters is brighter during solar maximum, but very significantly, there are more of these very bright areas on the surface of the sun. These are known as active regions, and we'll talk about that. Sunspots are located in those active regions. You'll also notice that during solar minima, which are the images at the top of the screen, the overall intensity of extreme ultraviolet light from the sun is much reduced. You can see it's darker, and there are very, very few of these active regions on the visible surface of the sun during solar minimum, which is likely to occur in about 7 years. So the effects that affect propagation don't stop with the sun. As these phenomena propagate through interplanetary space on their way out to the planets and beyond, many of these effects interact with one another. So in interplanetary space, before these effects ever affect the Earth or any of the other planets, the magnetic field of the sun has a very significant effect. The ejection of high-speed streams from coronal holes has an effect. We'll talk about that a little bit. And ejections of coronal mass, known as interplanetary coronal mass ejections, have very significant effects, especially during solar maximum years. And believe it or not, thermal radiation also has a significant effect. It causes winds, very significant winds at the high altitudes of the ionosphere, which causes a variability of HF propagation between the summer and the winter. And those are thermal effects which cause winds at very high altitudes. So this is kind of a cartoon that shows the Earth on the right and its magnetic field, and how that magnetic field is affected by these solar phenomena propagating through interplanetary space. So you can see those yellow arrows, those are the solar wind of magnetized, ionized gas, and also the interplanetary magnetic field, which is the magnetic field of the sun. And it's very, very intense at the sun, but by the time the interplanetary magnetic field gets to the Earth, it's about 10,000 times weaker than the magnetic field of the Earth. And thank God for that, because if the Earth's magnetic field were not so intense, there wouldn't be any human life possible on the Earth. And some of you may have read that one of the challenges of Mars exploration is going to be that there is no magnetic field on Mars, and all of these interplanetary phenomena are going to be a real serious challenge to human exploration on the surface of Mars, or on the moon for that matter as well, because there's no magnetic field on the moon to protect human beings on the moon. This very complex image I'm not going to attempt to read, but it just, this is a NASA image, and it just illustrates the incredible complexity of the physics of the Earth that are affected by the sun. And every one of these items here, probably a student, a PhD student, could probably do a dissertation on any one of the couple of dozen phenomena shown here. They're complicated and worthy of detailed study, but not, unfortunately, worthy of a lot of my time this afternoon, because there's just a limited amount of time for each of you to earn a PhD. So let's talk about the solar cycle in particular. So solar cycles are nominally 11 years old. They can be as short as 9 years, but most commonly they're about 11, and they could be 14 years or even a little bit longer, but that's not very common. The last solar cycle, the last complete solar cycle, was solar cycle 24. It ended in December of 2019. It had an interesting phenomenon illustrated on this graphic. Shown in green is the sunspot cycle for the southern hemisphere of the sun. And solar cycle 24, the southern hemisphere of the sun had a solar cycle that was offset by 2 years from the solar cycle in the northern hemisphere. It's unusual for the solar cycles to be, of the two hemispheres, to be offset by that much. And if you compare the green and the blue lines from solar cycle 24 to the green and blue lines for solar cycle 23, 11 years before, you can see they're distinctly different. The blue line for solar cycle 24, that was the northern hemisphere cycle, peaked in 2012. And then a couple of years later, when a lot of hams were worried that this was going to be an unbelievably weak solar cycle 24, the southern hemisphere peaked right up, and we had some pretty good, not great, but pretty good HF propagation 2 years later. It doesn't look like we're going to have that experience in solar cycle 25, and I'll show you the data in just a moment. So let's look at some of the forecasts for solar cycle 25. We're very close to solar maximum right now, but let me point out something important, and that is from the perspective of ham radio operators interested in HF operation. We care more about the 3 or 4 years near solar maximum than we do about the exact date of solar maximum. So during this presentation, when I refer to solar maximum, I'll be referring to the 3 or 4 year period of solar maximum, and we're in about the middle of that right now. It began, solar maximum HF propagation conditions began about 1 year ago, and they're likely to continue for 2 or 3 more years. So we've got a lot of fun ahead of us. These forecasts were produced by the Marshall Space Flight Center in Houston, Texas. They have a stake in this game because one of their many duties is to help protect human life and space. So one of their jobs is to predict dangerous conditions. So they have an important job to do, mainly having to do with manned spaceflight. And you can see this was downloaded from their website last week. And it shows their current forecast at the 50% probability level, which is likely to be correct, but it is a forecast. And there's also one that's very pessimistic. That's the one shown in red. Highly unlikely that that's correct, but they continue to publish this one. And there's one that's very, very optimistic that forecasts what conditions, what sunspot number might look like if the sunspot cycle starts to grow rapidly. There's no evidence that we're going to be on that very optimistic track, just as there's no evidence that we could possibly go back onto that very pessimistic track. So we're probably on the track where the green line is shown, the green curve, which suggests that the month of solar maximum is probably going to occur this year. But as I mentioned, that's not very important for us as communicators. So we're right in the middle of solar maximum right now, and we don't really care very much about when that month happens to be. This shows the same data, but from a different perspective. Instead of counting sunspots, instead this is measuring the radiation from the sun at a microwave wavelength of 10.7 centimeters. This solar flux index has been measured at an observatory in British Columbia, and it's simply a microwave dish pointed at the sun, and they measure the signal strength at a wavelength of 10.7 centimeters. Everything is very carefully calibrated so that the instrumentation maintains its exact same sensitivity throughout days, weeks, months, and years. So you can see that these curves are very similar to the sunspot number curves we saw before, but these are actually measuring this radiation of microwave energy. Now, some of you may have heard about the solar flux index, perhaps when you studied for an amateur exam, licensing exam, or you may have read about it. This solar flux index is not a direct measure of ionizing radiation. It's radiation that we can measure on the surface of the Earth, but it is not extreme ultraviolet radiation that causes ionization of the ionosphere. But we can measure it on the surface of the Earth, and we know from years of comparison that it is highly correlated to very good HF propagation. So this has been used for many years and will probably be continued for many years to come. So using a fancy word, this is referred to as a proxy or an alternative to measuring extreme ultraviolet light, which we cannot measure on the surface of the Earth. The only place we can measure it is in space. And this is a similar thing where the Marshall Space Flight Center shows how we've gotten to where we are now in the black line on the left, and that very light gray line just shows the month-to-month variations. The black line is called the smooth sunspot number. It's just averaged over a 13-month period. And then the colored lines show their prediction for the upcoming 7 years of solar cycle 25 as it goes through solar maximum and then goes down to solar minimum, which is likely to be about 7 years from now. And very similar to the last one, the 5% probability one, which is a very pessimistic track, is very unlikely. The blue track, which is a very optimistic one, which takes us to solar flux index numbers approaching 200, is also probably too optimistic, but not impossible. We're much more likely to be on the green track or maybe even the purple track, which shows us with solar flux numbers about where they are right now, around 160 or 180. The great news is that these are plenty big enough numbers to make 10 meters open every day from September through May. It's a rare day when 10 meters is not wide open. So, and you don't need a high class, extra class or general class license to operate 10 meters. There's plenty of spectrum there for technician class licensees, and you don't need extremely complex antennas to enjoy the 10-meter band. So we'll probably have a great year this year, great year next year, and then we'll start to decline sometime in 2025. So, as I mentioned on the very first slide, not only do we get beneficial effects from the sun 20 to 25 days out of the month, but for about 5 days out of the month, we get some of the very negative impacts, which I'll discuss in a little bit of detail later. This is a forecast from the Marshall Space Flight Center of some of those effects that degrade HF propagation. And similar to the other slides, these degradations appear to be following the green line on their forecast and not the pessimistic or optimistic track. So there's good news in this story, and that is because this is not an extremely intense solar cycle, we're getting the benefits on 10 meters of great HF propagation almost every day, but we're getting relatively few disturbed days. So if anyone talks to you about the heady days of 1957, when we had a huge solar cycle, ask them about the days that were really, really bad. And there were many of those as well. During this solar cycle, we're getting plenty of really good propagation on 10 meters. We've got much better equipment that no one could dream of in 1957, and we get very few of these badly disturbed days in this solar cycle. And we're not likely to get many more. This graphic shows the solar cycle track that we're on now on the right-hand side of the screen, compared to the last solar cycle. So the main theme of this slide is to show that the current solar cycle, where we are right now, is stronger, but not by a great deal, but somewhat stronger than the last solar cycle that peaked in 2014. But it is significant because even though this cycle is only a little bit stronger than the last one, we're getting much more good 10 and 12 meter propagation than we did 11 years ago. So that's a small increase has had a significant effect. And at the bottom of this slide is shown in the bluish green color is the sunspot cycle on the northern hemisphere of the sun and on the southern hemisphere of the sun. The important thing to notice here is that the sunspot cycles for the north and southern hemisphere of the sun seem to be more or less synchronized. So we're not expecting to get a double hump. And this shows solar cycle 25 in black and how it compares to all of the other solar cycles that have been monitored since the 19th century. And the important takeaway from this is that our current solar cycle has been rising more slowly than the very intense solar cycles that occurred in years past. And you can see that if you look at the lines for the solar cycles that had sunspot numbers above 200, all of them, without exception, rose more rapidly than solar cycle 25, our current cycle. So this current cycle is kind of a weak to moderate solar cycle. It's stronger than the last cycle in significant ways, and much weaker than the very strong cycles that occurred in the past. This graphic shows the hemispheric sunspot numbers. In green is the southern hemisphere of the sun, in red is the northern hemisphere of the sun. And the only important thing on this graphic is it appears that the two sunspot cycles, the northern and southern cycles, are in sync. And we're probably not going to see a double peaked maximum in this cycle. Okay, so let's move on to some other topics. So we've mostly discussed the really beneficial aspects of the sunspot cycle, but it's important to be aware of some of the other important aspects of the sunspot cycle. Let me see if I can suppress this. Okay. Just a moment. That's where I'll be. Coronal hole high-speed streams emanate from regions on the sun, and I'll show a couple of images of that in a moment. They emanate from areas of open magnetic fields. That is opposed to the areas on the sun that are closed magnetic fields. The sunspots shown in this graphic are closed magnetic fields. The magnetic fields go out into space a little bit and then come right back to the sun, whereas coronal holes are areas where the magnetic fields extend out into space, and it allows literally billions of tons of solar matter to escape into space. But don't worry, the sun is a massive star, and the loss of millions or billions of tons per second of solar mass has no effect on the future of the sun, except on the measures extending to many billions of years. So coronal hole high-speed streams are the most frequent source of minor geomagnetic storms throughout the solar cycle. At this part of the solar cycle, we're at solar maximum now. These minor storms have a relatively minor effect. But there's another type of explosive activity from the sun. They're called coronal mass ejections, always referred to as CMEs, and they can cause strong geomagnetic storms, and these are the ones that give us the 3 or 4 or 5 days of disturbed propagation during a typical month during solar maximum, coronal mass ejections. They can release billions of tons per second of solar mass into interplanetary space. So this is a couple of images. The one on the left side shows a very, very large Earth-facing coronal hole. And to give you an idea of the size of this, if the Earth would be to be compared with the size of the sun, it would be about 1/1,000,000th of the area of the sun. It's very, very tiny. But yet these coronal holes are huge. Maybe 10, in the case of this very large coronal hole, about 5 to 10% of the surface area, the visible surface area of the sun. So a huge amount of coronal material can be sent out into interplanetary space from this coronal hole. And the illustration on the right-hand side shows an illustration of open magnetic field lines, which allow all of this ionized gas to escape into space and into interplanetary space. And this is another illustration that compares coronal hole high-speed streams escaping into space from those very dark regions and the open magnetic field lines from the sun. And then sunspots, which always have closed magnetic field lines. So the solar material does not escape from sunspots. It escapes from these coronal hole regions. So during solar minimum, we tend to have relatively short duration minor geomagnetic storms. And because during solar minimum, we don't have a lot of ionization going on, so these minor geomagnetic storms are significant. But during solar maximum, where we are right now, minor geomagnetic storms have very, very little effect because there's so much beneficial ionization from sunspots in the regions of the sun adjacent to sunspots, that minor geomagnetic storms don't have a big effect over the next few years of solar maximum. However, we get long duration geomagnetic storms caused by coronal mass ejections. We'll talk about them in a little bit. So the coronal mass ejection, so the long duration minor geomagnetic storms during solar maximum don't have a very big effect on HF propagation, but the coronal mass ejections do. So this is a cartoon that kind of illustrates what's going on with the sun. The origin of all of this activity, both the beneficial ionization from sunspots and all of the problems from coronal mass ejections and from coronal holes, all of this activity is caused by the magnetic field, very intense magnetic field of the sun. And just to compare the size of the Earth to the size of the sun, it's just literally a pinprick, the Earth's surface compared to the massive, massive visible surface of the sun. So there's another phenomenon in the sun that causes very observable effects here on Earth. We all know from the seasons on the Earth that the Earth's rotational axis is tilted 23.5 degrees, and that's what causes winter and summer and spring and fall. So the part of the Earth we're on at mid-latitudes, this part of the year is facing away from the sun, and during the summer we're very much pointed at the sun. So we have very strong seasonal effects. Well, these same seasonal effects occur for HF propagation as well. And we'll talk about some of those seasonal effects in a little bit of detail later. But the seasonal effects occur not only because of the rotational axis of the Earth being tilted 23.5 degrees, the magnetic field of the Earth is tilted by 11 degrees. The North Magnetic Pole is up over Canada. And to further add to the complexity, the sun rotation axis is tilted 7 degrees with respect to the Earth's orbit around the sun. So as the Earth goes through its seasons, the interaction between the Earth's magnetic field and the interplanetary magnetic field also varies with seasons. By perhaps good fortune, those interactions are pretty closely aligned with the seasons on Earth, so they're a little bit easier to think about. We'll talk about that in a moment. So there's a couple of videos here. The video in the lower left-hand corner shows sunspots as they evolve over time. This video shows about a 5-day period as the sun is rotating. Recall that the sun rotates on about a 27-day period, and you can see how the sunspots evolve. In the upper right-hand corner is an image of a sunspot taken with a high-resolution camera, and you can see the dark center of the sunspot. The closed magnetic fields cause that area to be cooler than the rest of the sun, and that's why it shows black in this image. And the area surrounding the sunspot is where in the corona of the sun, this multi-million degree Fahrenheit area of the sun's atmosphere, where all of this beneficial radiation occurs, just outside of the very intense magnetic fields. And shown in the photograph in the upper left-hand corner is one of the largest sunspots ever seen compared to the size of the Earth. So that sunspot is just about the same size as the surface of the Earth. So this video on the left shows something called a solar flare. It's an explosive activity from these active regions on the sun. Almost all solar flares occur near solar maximum when the solar flux index is 90 or higher. That's mostly during the 4 years of greater solar activity near solar maximum, right when we are now. And these solar flares, if they're very intense, can cause total blackouts of HF propagation for up to 2 or 3 hours. But most of them are less than that. The radiation from solar flares that causes these blackouts is actually X-ray radiation, very powerful X-rays, and when they arrive at the surface of the Earth, at the lower levels of the ionosphere, an area known as the D region, about 60 miles over the Earth, it ionizes the D region so intensely that radio waves, HF radio waves passing through this D region 60 miles over our head get totally absorbed. And if you ever happen to be using an HF radio during one of these solar flares and one of the radio blackouts they cause, many hams have mistakenly thought that their radio had failed. There were literally no signals could be heard, especially on the lower bands, 40 and 20 meters. And it was actually caused by the sun and not by a failure in their radio. And you'll talk to hams maybe who've actually disconnected their radio and started trying to figure out what actually went wrong with it, and everything was perfectly okay. It was a solar flare, as shown in that video. The strongest solar flares are categorized as M-class and X-class. The X-class ones are the ones that cause the real problems on Earth. In the ionosphere, they can last for a couple of hours. This is a video showing the largest recorded ever solar flare. It's categorized as X28. And you can see the explosive activity that caused a complete HF radio blackout of more than 2 hours back in November 4th. And that was a very intense period of solar activity 2 solar cycles ago. And you can see on that little graphic on the right-hand side that there were, in the red line, 4 major solar flares that occurred between November 2nd and November 5th of 2003. Sometimes those are referred to as the Halloween storms, which occurred just after Halloween 2003. So coronal mass ejections are kind of the bad boy of disturbed HF propagation during the periods near solar maximum. And this graphic kind of shows the sun on the left with some sunspots visible on the surface, and this explosion of solar ionized matter, ionized gas exploding from the sun. And in this case, the cartoon shows that explosion heading directly towards the Earth on the right. And of course, the Earth surrounded by this very powerful magnetic field that allows human life to exist in the face of these intense coronal mass ejections. How intense are they? Billions of tons per second. Fortunately, a mere 50 tons per second arrives on the Earth, so that's a whole lot less, but it's still a significant amount. But the probabilities are that most of these coronal mass ejections miss the Earth. Either they occur, let's say, from the backside of the sun or from near the east and west limbs, and they miss the Earth. So the most serious effects occur when a coronal mass ejection happens to occur when it's pointed directly towards the Earth. But the magnetic field of the Earth, 10,000 times stronger than the interplanetary magnetic field, protects us. So our lives are not at stake, but our radios might not be very happy for a few days. This video shows one of those fast coronal mass ejections taken from a satellite. So you can see that the coronal mass ejection in this case was not directly east-west. It was oriented somewhat southward, probably not affecting the Earth. So the most severe effect of a coronal mass ejection occurs when the magnetic field that couples the sun and the Earth and all the other planets, it's called the interplanetary magnetic field. When that magnetic field is oriented opposite from Earth's magnetic field, and an effect called reconnection occurs. So let me just take you back in time to when you were in elementary school. And you may remember you probably conducted some simple science experiments with horseshoe magnets. And I'm sure you remember that when you orient the horseshoe magnets so they have opposing magnetic fields, they drive each other apart. And when they have magnetic fields, when the magnetic fields are in the same orientation, they drive each other apart. But when you flip one of the horseshoe magnets in the opposite direction, it causes the two magnets to very strongly attach to each other. And the very same thing happens with coronal mass ejections from the sun. When the orientation of the sun's magnetic field as it arrives on Earth is opposite from the Earth's magnetic field, then there's a very strong attraction that causes these ionized gases to have a very big effect on the ionosphere. So, and about half the time, the interplanetary magnetic field is opposite from Earth's, but there's about a 50% chance that it'll be the same as the Earth's magnetic field. And when that happens, the Earth's magnetic field is very, very efficient at pushing away the effects of these coronal mass ejections. So in order for all of these ionized gases from coronal mass ejections to have a big effect on the Earth, a whole bunch of things have to happen exactly kind of in the wrong way. The mass ejection has to be oriented towards the Earth. There's a fancy name for that called geo-effective. Most of them are not. And even those that are close are usually near misses. But even for those that are a direct hit, it's only when the interplanetary magnetic field is oriented opposite to Earth's field that we get the big effects. And those can be pretty dramatic, but they're pretty rare also. Okay. About a half a dozen slides back, I showed the seasons on the Earth that we're all familiar with living here, but they were kind of also magnetic seasons on the sun. And they have effects that cause coronal mass ejections to be much more severe during our equinoxes around October and March than they are at the rest of the year. Looking at solar maximum, the really significant effects of solar maximum begin almost exactly a year ago, when 10 meters and 12 meters started to open wide open all around the world. And that's been continuing now for about a year. And it's probably going to continue for the next 2 or 3 years. And 20, 30, and 40 meters are also beneficially affected, especially throughout the night. 160 and 80 meters, on the other hand, are somewhat degraded. And if we look at the with the various HF bands and which ones are most beneficial at this part of the sunspot cycle, 17, 15, 12, and 10 meters are very significantly improved over the last year, and that's going to continue for perhaps for another 3 years. 20 meters is also improved, but especially at night. And we're getting some incredibly good propagation on 20 meters during the middle of the night, when just a few years ago, 20 was completely dead at night. And 40 meters also is a much more reliable DX band throughout the night at this part of the sunspot cycle. 80 meters is sometimes a good nighttime band, but you have to be there on the right days. A lot of days it's rather poor. 12 and 10 meters are kind of the magic bands to be on at this part of the solar cycle. This is wonderful for very basic ham stations. You don't need very much power or very sophisticated antennas to really enjoy 12 and 10 meter propagation at this part of the sunspot cycle. So if anyone hasn't yet taken your radio and gotten on the 10 meter band, boy, this is really the time to do it. And you don't need very much. A mobile station will work. Some people have made contacts halfway around the world with handheld radios on 10 meters. Of course, if you have better antennas and more power, propagation becomes more reliable for you, but it's not necessary at this part of the cycle. 17 and 15 meters are also more reliable bands for DXing than they were a few years ago, but the effects are not as dramatic as 10 and 12 meters. 10 and 12 meters were mostly dead bands until about 1 year ago today, but 17 and 15 stay useful throughout the solar cycle, but they become much better during solar maximum. 20 meters is open essentially all day and all night, except in the summer. In the summer, it's almost exclusively a nighttime band for DXing. And this is where very high altitude winds come into play. During the summer, just like here, might be hard to remember that today when we're having one of our record cold days of the year. But during the summer, we have these very hot days, and at high altitudes in the ionosphere, it gets very hot indeed. And that heating causes intense winds that blows a lot of the gases that we need for the ionosphere, blows those gases over to the night side of the Earth. So even though you would think, gee, in the summer, we're pointed right at the sun, the ionization should be greater. But these winds that get developed from heating degrade the daytime propagation compared to this time of year. But on the other hand, because these gases, mostly oxygen, get blown over to the night side of the Earth, nighttime propagation is great in the summer. Daytime propagation is not as good as it is this time of year, and that's because of heating. 40 and 30 meters are great nighttime bands. 30 is a great band if you don't have access to really good antennas or high power amplifiers. In the United States, we're limited to 200 watts, and very few people have sophisticated antennas on 30 meters, and it's a great nighttime band, as is 40 meters. But there are a lot more hams on the 40-meter band with really good antennas and higher power. So it can be a little bit challenging, but both 40 and 30 are great bands at night. And 160 and 80 are degraded by this sunspot cycle. 160 meters is particularly challenging, and for the most part, it's only the real 160-meter stalwarts that are really sticking with that band. 80 meters is better, but still nowhere near as good as it was just a few years ago. But there is the occasional day, even at solar maximum, when 80 meters is very good, but they're far and few between. So I'm getting to my last couple of slides. I promised I'd be under an hour, and these are the last two slides. So you probably have an idea that this propagation stuff is really, really complicated, and it really is. And a lot of it is unpredictable. But you know, we're in the internet age when we all have computers, we all have access to the internet, and now we can use a technique referred to as nowcasting to understand exactly what's going on with propagation without having to understand all these complexities that we've just scratched the surface of. And although a lot of this complexity is embedded in propagation forecasting software, it's far from perfect. So what do I prefer? I prefer nowcasting techniques, and there are several websites that you can access that allow you to see exactly what's happening with propagation all around the world. This website is primarily for CW stations. So the red dots on this map, on this web page, show where the receivers are located. And the green line shows, I'm sorry, and the blue dots show where the transmitters that those receivers heard are located. So if you look at the green lines, they connect blue dots in Europe, in this case, to red dots in North America. And you can see the actual propagation that's occurring in near real time. So you don't need to understand all this propagation stuff. You can go to this web page and you can see right now what propagation is happening on the HF bands. This is a very easy website to use. There's some radio buttons in the middle of the page where you select the band you want to look at. And you can also select the mode. Usually you select CW, but you can select radio teletype also. And then at the bottom of the screen, you can select if you just want all of the activity to be shown. In this case, I selected at the bottom of the screen on the left side, I selected North America for the spotter receiving stations. And on the right-hand side, for the blue transmitting stations, I selected Europe, and that's why this map shows only stations from Europe that were heard in North America. It's a very easy web page to experiment with. You can't break it, so you can experiment with it. If you make mistakes, it doesn't matter, but it's very useful to get familiar with this. And another thing that is especially helpful with a website like this is you can get on the air on CW and call CQ. This website, the receivers on the associated with this website, shown in red, are looking for stations calling CQ. So if you get on the air with your call sign and call CQ, and then put your call sign in the spotted DX block at the middle right side of the website, it will report all of the receivers that hear you. So you'll not only know what propagation is there, you'll know exactly which of these roughly 100 receivers are hearing you. Very, very handy, and can be very surprising when you do it to see where in the world your signals are being heard now. And this is my last slide. I really like this webpage. This is reporting not only CQs, but all of the contacts being made worldwide on the digital FT8 mode. And it's showing receivers all over the world, and in the red lines are showing transmitters and where they're being heard. And you can see this was 20 meters at 2200 Zulu, so this would be about 5 p.m. And you can see tremendous amount of activity on the digital FT8 mode between North America and Europe. And just like for the previous web page, you can also get on FT8 and call CQ or call some stations. And when you are being heard, your call sign will appear on this page, and you'll be able to see your propagation. It's very handy. You can enter your call sign on this web page. Just go ahead and use the web page, experiment with it. You can't break it, and it's a fantastic tool. So this is the end of my presentation. I know it's been extremely complicated. I'll provide a PDF of all of these slides, so you can either send me an email and I'll send them to you directly. I'll provide them to Alex too, and maybe they can be distributed that way. So that's the end of my presentation, and if there are any questions, I'll be happy to answer them, or you can email them to me.
Okay, well, great. Thanks for that terrific presentation, Frank. And if you don't mind, we'd like to post your slides along with a copy of your video on our webpage so that everybody can find it there.
That's fine. And I will, I made a few minor changes to the slides over the last few days, so I'll send you the most current version in a few hours.
Great. That sounds wonderful. Thank you. So we have some questions. So go ahead, John.
Yeah, Frank, great presentation. Do you have any advice for a ham in Maryland who wants to work a station in China or India?
Well, you couldn't pick a better part of the solar cycle to do it. The best way to do that, first of all, is to focus on the 10-meter and the 12-meter band, because you don't need a lot of power. You don't need big antennas to do that. And those bands are open to China and India every day. It's not directly related to my presentation, but you can use some of the DX spotting websites so that you can look for stations in India or China that are being reported that way. and then you don't have to, keep searching around for them. So I would suggest using the DX spotting websites. A very good one is the VE7CC website. And again, just like the other websites I showed, you can't break that website. So you can practice using it to look for stations in India, which is the VU prefix, or in China, which is a whole series of prefixes beginning with B as in Bravo. Bravo Yankee is, and Bravo Alpha are two of the common ones. So what I would suggest is 10 and 12 meters, and use the VE7CC website in order to figure out what stations are actually active right now. Sort of nowcasting, not only for propagation, but also for actual ham radio activity right now.
Okay, John? All right, thanks. Zori?
Thank you. Frank, another beautiful presentation, as always. I wonder if I could ask you to go back to your next to last slide. Yeah, one of the things that I noticed is that a number of those receiving and at least two of the transmitting stations appear to be right on the gray line. And I wonder if that was something that you might have wanted to point out, or perhaps I'm the only one who suddenly realized that.
Yeah, so Zori, you've sat through a lot of these presentations that I've given. They're all a little bit different. This particular slide was taken on shows nowcasting data on the 80-meter band. So the 80-meter band is very much affected by sunrise sunset considerations. And it was also at 0500 Zulu, so that's midnight. So sun was coming up in Eastern Europe, as you can see on the map, and it was a couple of hours away from Western Europe. So it wasn't so much gray line in this case. It was more that there are some enhancements to 80-meter propagation as sunrise approaches. So that's a little bit of what you're seeing, but keep in mind that there's an awful lot of ocean between Europe and North America, and if there were stations active from ships there, we would see more blue dots. So this is biased a little bit by the land mass that happens to be there. If I had taken this image 2 or 3 hours earlier, well, first of all, it would have been the middle of the night in Europe, so there wouldn't have been as much ham radio activity. So you're seeing a lot of effects here. You're seeing sunrise when people get out of bed and get on the air. So you're seeing that, just more activity. And you're seeing the effects on 80 meters during daylight. That's why you don't see any blue dots to the east of Turkey and the Ukraine, because they're in broad daylight. So it's kind of fun. Just like you tried to analyze this slide as to what's going on, it's kind of fun to look at this nowcasting data, either from the reverse beacon net, which is where this website is, or from PSK Reporter, and you can see all these propagation effects. It's really neat, and try to figure out exactly what's going on. So the only thing I'll say is this was not a gray line phenomenon. Otherwise, it would have followed that day to night transition. This is just the normal effects of sunrise on human activity as well as propagation on the 80-meter band. But that was a good stab at that, Zori.
Thank you, Frank. I always learn from your presentations.
There's a lot to be learned. You can earn your PhD in any one of these narrow topics if you want to pursue that.
Sounds good.
Okay, great, thank you. Are there any more questions? All right. Well, thank you again, Frank, for taking time out of your busy schedule to be with us and to, give us all this great information. This is also very useful as we head into field day. So it kind of informs us on just practical matters of bands and things. So thank you very, very much.
Yeah, it's field day is a lot of fun, and you really get to observe a lot of propagation effects because there's so much activity, tremendous amount of activity on field day. So, and I'll do a little advertising. The members of the Montgomery Radio Club are very welcome to attend my annual open house. We've been doing that for about 35 years now, and it's always on the Saturday before field day. And it's not so far from Rockville to Western Howard County. So if any of you want to visit this station and get a tour and meet some of the other active hams in this part of Maryland, you're always welcome to join in the fun. Starts at noon on the Saturday before field day here in Glenwood, Maryland.
That sounds fabulous. I'll email you to get particulars, and I'll share it with our club if that's okay with you.
Yep, and several radio clubs hold their meetings here also on that day.
Ah, wow. You really are inclusive with all that you have and the time that you donate and all your resources. Thank you.
Over 100 hams show up for that event every year.
Wow.
It's a lot of fun. Okay, well, it was my pleasure to present this extremely complex topic. Because of the complexity, it's a lot of fun learning about this and then just getting on the air and enjoying it and trying to figure out how I was able to make this contact halfway around the world on 10 meters with 5 watts and a piece of wire. But you can do it. You just have to get on the air and play with it.
Sounds great. Thank you, Frank.
Okay. 73.
73.